This video is about titration, which is an important chemical analysis procedure, a quantitative analysis procedure that's used a lot in chemistry. It measures volumes of liquids and then uses that to determine moles. So in order to make that connection, you need to use the concept of molarity that you just learned about. The type of quantitative analysis that's done with titration is called volumetric analysis because you're measuring volume. It uses a device called a burette, and a burette is basically a long, thin, graduated tube that has a valve at the bottom. This valve has a particular name. It's called a stopcock, and the valve can be either completely open, completely closed, or you can sort of feather it to make partial drops come through. The markings on here that indicate volumes go from 0 at the top to some higher number at the bottom. So this tool isn't designed to measure how much liquid is in the burette. It's designed to measure how much liquid has left the burette. So you take a starting and an ending measurement, and the difference between the two is how much drained out the bottom. What goes inside the burette is something that's called a titrant, and sometimes this titrant is a standard solution, and that means a solution of known concentration. Sometimes the titrant is unknown concentration as well. Another term that's used in describing titration is endpoint. The endpoint is the point in the titration where a visual cue, like a color change, or an instrumental cue, like a reading on some kind of a meter, will tell you that you've just used up one of the reactants and changed limiting reactant to the other reactant, which means the reaction has just completed. Here's how it works. The first thing that happens is one of the solutions is placed in the burette. So this solution is called the titrant. It may be standard, it may be something that you know, and it may not be. Next, a sample of the other solution is placed in a flask below the burette. Now this might be the standard, many times it's not. Then you open the valve and you watch for a cue. And titrant is carefully added until the endpoint is reached. When the endpoint is reached, often there'll be a visual cue like a color change that we saw happening here that will tell us that we're at the endpoint. The next thing you do is look at the burette. You knew its starting volume, you know its ending volume reading, and the difference is the change in volume or the volume that was delivered out the bottom of the burette. Then finally, we use stoichiometry to determine what the concentration was of the unknown, whether that unknown was in the flask or in the burette. Let's take a look at the stoichiometric calculations that go along with a typical titration, and then I'll show you a little video of a real-life titration with its results, and then we'll do one more example problem. So here's our example. A 15 milliliter sample of H2SO4 is titrated against our standard 0.147 molar NaOH solution. The endpoint is reached when 36.42 milliliters were put into the flask from the burette. So the question is, what's the concentration of the H2SO4? In this titration, I'm going to draw a little picture here to sort of indicate what's happening. Here's my burette with its stopcock, and in the burette is my standard solution. It's a 0.147 molar solution of sodium hydroxide. And in the flask below it is some H2SO4. I know what the volume is. This is 15.00 milliliters. I know that it's H2SO4, but what I don't know is what is its concentration, and that's my objective. I do know that when the endpoint is reached, when I've just used up all the H2SO4 in the flask, I have added a volume of 36.42 milliliters of my standard solution. Well, the first thing I have to do, because this is stoichiometry, is I'm going to have to find out what's the balanced chemical equation that describes what's happened here. And here's what it is. I have 2 NaOH plus H2SO4 producing water, that's H2O, and there'll be a 2 in front of here when it's balanced, and a salt. And that salt in this case will be Na2SO4, and that aqueous salt will not show up. What can I do with the information that I have? Well, I know that 36.42 milliliters of my solution reacted. Here's what else I know. I know that there were 0.147 moles of NaOH in every liter of solution. Now what I'm going to do here is I'm going to leave the milli part there and just allow the liters to cancel. So now I have millimoles of NaOH. But there's a mole ratio here from the balanced chemical equation that can help me, and that is that 2 moles of NaOH reacts with 1 mole of H2SO4. And since I just used up all the H2SO4 when I added this amount of NaOH solution, this calculation, when moles of NaOH are canceled out, will tell me how many millimoles of H2SO4 must have been in the flask. When I do my calculation to 3 significant figures, I get 2.68 millimoles are in the flask. So my objective is, what's the concentration? And that's number of moles divided by liters. Well, in this case I have millimoles, so I'll take 2.68 millimoles of H2SO4 and divide by 15.00 milliliters, because that's what his volume was. The milli part cancels out now, and I have moles per liter, which is molarity. To 3 significant figures, my answer is 0.178. I'm about to show you an example of a titration. So I'm going to introduce you to some of the tools that are used in a titration. This tool here is called a burette. It's a long, skinny cylinder, and it's got markings on it that measure volume. They don't measure volume that it contains, but volume that it delivers. You can see that it's marked every 1/10 of a milliliter, so that means you should be able to read it to the nearest 100th of a milliliter by estimating between the lines. At the bottom there's a valve. It's called a stopcock, but you open it up and it allows liquid to drain out, close it, and then stops it. Typically you'll place underneath the stopcock a flask or something to catch what comes out. Here's my titration that I want to do today. I'm drawing a picture of the setup here to kind of get a mental clue of what's going on inside the physical hardware that we've got here. I am going to put into the burette some 0.833 molar acetic acid. So this is something that somehow I've determined ahead of time what its concentration is. That's my known, that's my standard solution, and it's also my titrant. In a flask underneath the burette, I'm going to place a solution that has an unknown concentration. I don't know what the molarity is, but I do know that its volume is 30.0 milliliters. And it's something that reacts with the acetic acid. It's a weak base, and in fact the weak base is ammonia, which is NH3. Here's what will happen inside the flask. The acetic acid will react with ammonia and neutralize it. It's an acid-base reaction, and you should get water and a salt. We're leaving the water out of this, and the net reaction gives ammonium acetate, which is the salt. Now you won't see any ammonium acetate because it's aqueous, just like you won't see acetic acid or ammonia. They're all individual molecules in solution, and they all happen to be colorless as well. So you can't visually tell what is where at any given time. But what we're going to do is we're going to add something called an indicator. And when we study acids and bases, you'll learn more about this. But we're going to put an indicator in here that makes this look pink when it's a basic solution. And then if it turns acidic, then it will look colorless and clear. Well, this allows me to figure out when I've just used up all the ammonia, because it'll look pink as long as there's any ammonia in there at all. When the very last bit of ammonia gets used up, the next drop of acid that I add in there will put a whole bunch of extra acetic acid. With that extra acetic acid, will suddenly change the color from pink, the base color, to colorless, which is how we indicate that it's an acid. That's how I'll know that I've just used up all the ammonia. Now, to prepare for this titration, there are a few things that I've got to get ready with. One is, at the business end of this thing, where the valve is, there's air in the tip, and everything that comes out of there gets measured. I don't want to measure air. I want to measure only the acid that I'm dropping out of here. So I'm going to open the stopcock and allow just enough flow to make sure that the tip is completely filled with liquid, and then I'll stop it. Here's something else I need to change. My liquid level, I have to measure it at the start and at the end to know how much came out. And right now I can't measure it because the meniscus is above the numbers. It's not measurable. So I'm going to have to drain a little bit more out to make sure that I get that liquid level down below the 0 or right at the 0. It's a waste of time to try and stop it right at 0. Just make sure you drain it down so that it's below 0, and then you can read a starting volume. A few things about reading these burettes. You want to read the bottom of the meniscus, for one thing, and the other thing is the numbers get bigger as you go down because we're measuring how much has gone out. So this looks like it's not quite 1. I'm going to call it 0.97 milliliters. That's my starting volume measurement, and I'll make a note of that. I'm almost ready to begin titrating, but I have to remember to put my indicator in there because if I don't, the whole thing's going to look colorless the whole time and I'll miss my endpoint. So I'm selecting an indicator called phenolphthalein. It looks pink, as I said, when basic solution. I just added a couple of drops, I swirl them around, and now my solution looks pink. Now it's not going to be easy to see this color change against that black lab bench, and so I'm going to slip a piece of white paper underneath there to increase the contrast, and this will make it a lot easier to see when it changes from pink to colorless, because it'll happen fast. Okay, everything is ready, and now I can start draining acid into my burette. I'll drain a little in there. I'm not exactly sure where the endpoint's going to be at this point, and swirl it around, and it's still pink. So I'll put a little bit more in there, stop draining it, swirl it around. Now, the closer and closer you get to your endpoint, the longer it's going to take to become certain what color it is. So you end up going very slowly, and this takes a long time. So I'm going to sort of clip a lot of this time out, and I'll talk to you next when we get close to the endpoint. Okay, I'm at the point now where I'm quite close to the endpoint. You can see that there's a slight pinkish tinge to the liquid, but it's not nearly as pink as it was when I started. I'm very close to the endpoint, and now I'm just going to add very small quantities at a time. Did you see what just happened there? I had a solution that looked very faint pink after adding a few drops at a time, and then down to 1 drop, and then to even fractions of a drop. And then I added a small part of a drop, and it changed from the faintest pink into something that's not pink at all. I've just reached my endpoint. Now I need to measure what's the final volume reading so I can tell how much got delivered out of there. I'm reading at the bottom of the meniscus, I'm measuring to the nearest hundredth, and I'm going to call that 26.99. It's almost touching the 27 line, but not quite. Okay, here are my starting and ending volumes. I started out with a 0.97 milliliter reading, and I ended up with a 26.99 milliliter reading. Remember, the reaction that was happening was the acetic acid was reacting with ammonia that was in the flask. Acetic acid was a titrant, and it was making ammonium acetate. I need to use stoichiometry to figure out how much NH3 was there based on how much acetic acid went into the NH3 to use it up. Well, to find out the volume of acetic acid solution released, I just take 26.99 milliliters and I subtract from it my starting volume, 0.97 milliliters. Well, that gives me 26.02 milliliters of solution delivered. Starting from there, I want to do a stoichiometry calculation that ends up telling me moles of NH3. Here's what I know about my NH3 solution. It has 30 milliliters in it, so if I just know moles, I can divide by volume and get my concentration. So 26.02 milliliters times 0.833 moles of acetic acid per 1,000 milliliters is going to give me moles of acetic acid. The stoichiometry is 1 to 1 here, so I have 1 mole of acetic acid reacting with every 1 mole of ammonia. So if I look at what I've canceled out now, it's milliliters and moles of acetic acid. Now I have moles of NH3, which was my target. That's what I was looking for. When I do my calculation, I find out that I had 0.0217 moles of ammonia in that flask. So what was the concentration of my ammonia in moles per liter? Well, I had 0.0217 moles, I just calculated, in 30 milliliters. I can easily convert this into moles per liter by just multiplying by 1,000 milliliters per liter, and this gives me moles per liter, or molarity. 0.0217 divided by 30, my answer is 0.722 molar. So now I know the concentration of my unknown. And that's how titration works. There are different kinds of titration, but this acid base is a pretty good way to get started and become familiar with how it works. Here's another example titration. This doesn't involve two solutions, but it involves something that can be turned into a solution. It says all the iron in a 2-gram sample of an iron ore exists as Fe2+. This ore is dissolved, so that makes it into a solution, and that means you can titrate it. And it's titrated against a 0.1 molar KMnO4 solution. The titration requires 26.45 milliliters of KMnO4, so that's what came out of the burette. And there must have been a visual indication what percent of the ore was iron, and then the net ionic equation is given to you. Now this is a redox titration, so you're going to have to balance a redox reaction to get this task completed. Before I do anything, I think I'm going to balance my redox reaction. MnO4 minus is going to Mn2 plus. That's got to be one of the half reactions. And in fact, this is a reduction, because if I assign oxidation numbers here, I see that the manganese is 7 plus when it's in permanganate, but it's only 2 plus here. So that's one of my half reactions. The other half reaction is Fe2 plus going to Fe3 plus, and that's obviously an oxidation. Let me balance the top half reaction. The manganese is okay, but I need 4 waters to balance my oxygen on the right. That gives me 8 H pluses that I need on the left to balance the hydrogen. 8 pluses and a minus is 7 pluses, and the right-hand side is 2 plus, so that means I need 5 electrons on the left-hand side. Fe3 plus is 1 plus higher than Fe2 plus, so adding 1 electron to the right-hand side will balance that. To make the electrons lost and gained the same, I have to multiply the bottom equation by a coefficient of 5. And when I add it together, this is what I get for an ionic equation. 8H plus MnO4 minus plus 5 Fe2 plus makes Mn2 plus, 4 water, and 5 Fe3 plus. Now what's going on with my titration? In my burette, I have a 0.1000 molar solution of KMnO4. But KMnO4 is going to split up this way. It's going to give me K pluses and permanganate ions in a 1-to-1 ratio. Potassium is a group 1 salt, so of course this would be soluble. The amount of this that I see delivered here, it says, is 27.45 milliliters. In the flask, well, I've dissolved this ore into some solution, and I don't really care what its volume is, but I do know that I have some Fe2 plus in here. I've dissolved 2 grams of ore. I want to know how many grams of iron were in there. Stoichiometry is going to help me get there. My starting point is what I know from the titration. 27.45 milliliters of solution were dropped in there. Now in this case, I think I do want to change this into moles and not millimoles. So I'm going to put the concentration next, 0.1000 moles of permanganate per 1,000 milliliters instead of a liter. And that allows my milliliters to cancel out. My mole ratio, well, every 1 mole of MnO4 minus reacts with 5 moles of iron 2 or iron 3. Since I want mass so I can compare with the mass of the ore, I'll multiply by the molar mass of iron, which is 55.847 grams per mole. Now, some of you might object to this, and you might say, well, look, this isn't iron, this is iron 2 plus. But you can still use this molar mass, and here's why. The only thing that's different between elemental iron and iron 2 plus is the iron 2 has lost 2 electrons. Well, electrons really don't weigh that much. So little, in fact, that we can ignore it. And this will give us a mass of iron that was in that sample. When you do your calculation, you should have 4 significant figures, and it's 0.7665 grams of iron. Our objective was to find out what percent was iron, so we'll take the mass of iron, 0.7665 grams, and divide by the total mass of the ore, which was 2.000 grams, and then just multiply by 100 to express that as a percent. And it comes out that 38.33% of the ore was iron.